Hi friends, welcome back to new session. So I think in the last sessions we started armature reaction and we had taken some sessions regarding armature reaction. Now let us see. I already told you because armature reaction you are going to have two effects. Number one is the demagnetizing effect. Number two, cross magnetizing effect. So I think to reduce cross magnetizing effect, we went for a shifting brush along MNA, but that was the outdated method. Nowadays we are using interpole windings. And if you see in the last session I explained waveforms also. Now let us see in this session, let me discuss regarding compensating winding. See guys, as I told you, because armature reaction you are going to have two effects. Number one, demagnetizing effect. Number two, cross magnetizing effect. So please tell me, demagnetizing effect means what? Your resultant flux will mean your net flux will reduce, no? Okay. So guys, if we try to see in the EMF equation of DC generator, E is equals to formula pi Z N P by 60A. In that formula, so please tell me what is the nomenclature for this pi means is the average value of flux per pole. So let me write that. Pi means what I said, average value of flux per pole. Per pole means, please try to understand, per pole average value of flux per pole means, try to let me show you with by using laser pointer in this region. Per under north pole, average value of flux per pole. Under south pole, average value of flux per pole. That means so average value of flux per pole reduces here. Okay, that means along d axis. Already you know, so axis which is passing along the poles can be called as what? Axis which is passing along poles can be called as d axis, no? Direct axis, d axis. Okay, that means if you want to reduce demagnetizing effect, okay, that means if you want to reduce a reduction of average value of flux per pole, that means we need to do some compensation along d-axis, okay. That means whatever my discussion regarding a reduction of your demagnetic effect, so that has to be done along d-axis, along direct axis, along polar axis, because I need to improve average value of flux per pole. Per pole means you have to discuss about, you have to consider d-axis, you have to consider polar axis, okay. So in this region, okay. So here what I am doing for reducing demagnetic effect means we are using compensating winding. What is that? We are using compensating winding. Already we know in the previous session we explained. So this cross under north pole, dot under south pole, nothing but direction of armature current. So if direction of armature current is cross, so if by using right hand thumb rule, so if let me show thumb direction of current, so if you show thumb into the board, direction of armature flux will be clockwise. This blue color flux lines indicates direction of armature flux, okay. And here, so let me show thumb for the direction of armature current, which is coming from the laptop, or I can say from the board. So direction of our rapid fingers indicates direction of armature, direction of armature flux. So it will be anti-clockwise direction. So here our motto is to reduce DM effect. So please try to understand, because how we are getting, why you are getting this demagnetizing effect? Because of armature reaction. What is the definition for armature reaction? Effect of armature flux on main flux is called armature reaction. That means because of armature flux only we are having armature reaction here. So here what we are doing is, in this main poles, in this main poles, I just provide some slots. Please try to let me show you laser by using laser pointer. Yes, here I just made some slots. Here. See, try to see under north pole also, and north pole shoe. I just made some slots here. So in this example, I have taken 1, 2, 3 slots. Here also I have taken 3 slots here. So and in this pole shoe, I'm just placing some conductors. Those conductors only can be called as compensating conductors or pole phase conductors, because we are placing the conductors in this pole phase, or I can say pole shoe. Okay. So why we are placing this compensating conductors means, yes, to neutralize armature reaction. To neutralize armature reaction. So let us see how. See, this compensating winding is connected in series with the armature. Okay. So please let me highlight the points which I explained here. Yes, by using this highlighter. First of all, the compensating winding is placed in the slots of pole shoe. Okay, pole shoe. And what I am saying here, composite is connected in series with armature winding, and connections are made such that so whatever the flux we are getting because of armature current, this pi a armature flux pi, armature flux pi a. So because of this compensating winding current, whatever the flux you will get, that flux has to oppose your armature flux. So like that you have to make some arrangement here, okay? Such that it neutralize armature reaction means, so I told you already, because of armature flux only we are getting armature reaction. So if you take under north pole, armature direction of armature flux is a clockwise direction, you make whatever the flux due to compensating winding, that flux should be anti-clockwise direction, okay? So I think please try to see, I'm just using some different color for this. So already here it is there, yeah. So this should be direction of compensating conductor flux. Okay, yeah. It should be what I'm saying. It should be anti-clockwise direction like this. Okay. So now please tell me, guys, if you want flux due to compensating conductors in anti-clockwise direction. So by using right hand thumb rule, please tell me what might be the direction of compensating winding current. It should be out of the board. It should be out of the board. Please try to understand. Just try to show your rapid fingers in the direction of your flux due to compensating conductors, and thumb indicate the direction of current in compensating conductor should be out of the board. So out of the board means what? It should be dot here. It should be what? Dot. Okay, it should be dot. So please be careful. Here direction of armature current is cross and direction of compensating winding current is the dot. So like that you have to make arrangements, okay? And direction of armature flux is clockwise. Direction of flux due to compensating conductor is the compensating conductor current is I can say anti-clockwise direction. Okay. So here also if you see under south pole, direction of armature current is dot, and direction of current in a compensating current should be cross like this. It is nothing but cross here, cross, cross, cross. Okay. And if you see direction of armature flux here is anti-clockwise direction, and it should be what? Direction of flux which is due to current flowing in a compensating conductor should be, you can say, clockwise direction. Okay. So here, so whoever the responsible for having armature reaction, I can say armature flux, that is neutralized here itself. See, try to understand. So let me use a different color. Let me use white color here. Yeah. This armature flux is neutralized by flux due to current flowing in composite conductor here itself. See, is there opposite direction? No, they are opposite direction. So I can say compensating winding nullifies effect of armature reaction. So it is opposing your armature flux. But try to understand, this effect is there only in a polar region. That you should not forget. Okay. Compensating winding nullifies effect of armature reaction only in a polar region. That means only in a along, I can say along a, I can say d-axis, along d-axis, okay, but not in interpolar region, okay. So guys, here there is very important point. So compensating winding is connected in series with armature winding. Connections are made such that it neutralizes armature reaction. So very important point. And the compensating winding nullifies effect of armature reaction only in polar region, but not in interpolar region, okay. And see here, I'm just giving some nomenclature for try to understand here. So you please try to see, I'm using a white color for understanding this part. This part, see. Can you please tell me what about this one? Can you please tell me what about this distance? This distance, I'm saying, this distance. So to be frank, this is nothing but pole arc, no? This is nothing but pole arc. So I can call this distance as pole arc, okay, pole arc. And please tell me, you know already pole pitch means slots per pole. What is that? Slots per pole. Slots per pole. Example, see here under North Pole, how many number of slots are there? See, slots per pole means you have to see, the slots, nothing but in which armature conductors placed, not this composite conductors. Okay, so here slots per pole means, let us try to see here 1, 2, 3, 4, 5. In this example, 5 slots are there per pole. That means, please try to understand. Here in my example, your pole pitch is this distance. So let me show you. Yes. Yeah. So this, if you see this portion, you can see this portion comes under category of, I can say, pole pitch, because I told you pole pitch means what? Slots per pole. Slots per pole. Slots per pole. Okay, slots per pole. So please tell me here, if you try to understand clearly, do you think that here pole arc and pole pitch distance is same? No. So to be frank, pole arc is the distance is lesser than, I can say, pole pitch. So I can write here pole arc by pole pitch. Pole pitch, it will be around 0.7 to 0.8. It depends. Okay. Approximately I can take it as 0.8, or I can say you can take 0.7 also. Okay. That means, what is the meaning for that? Your pole arc covers 80% of the pole pitch distance. That means, in this pole arc, in this pole shoe only, we are placing a compensating winding. Okay. So I am asking one simple question here. So whatever the composite conductors we are using here to neutralize armature reaction, so this effect is restricted only to 80% of your pole pitch. Please try to understand that. That means, see, it is not neutralizing armature reaction. It is not completely neutralizing armature reaction. Try to understand, because example, in this distance, I just placed 4 slots. I mean 5 slots here, but here I'm having what? 3 slots. That means if I place here 5 conductors, 5 armature conductors, I'm having here what? 3 composite conductors only. So try to understand that. Pole arc covers 80% of the pole pitch distance means effect of, I can say, compensating winding. I mean compensating winding and neutralize armature reaction. Its effect is there only I can say 80% of the pole pitch distance. Try to understand that. Okay, this is very important. So examiners point of view, it is very important. Okay. Okay, and let me see here this point. Let me take composite conductors per pole. I'm just taking it as ZC. Okay, can you please tell me in this example, suppose if I place one conductor in each slot. So here 1, 2, 3. 3 composite conductors are there per pole. Like that, I'm just saying composite conductors per pole. I'm just taking it as ZC distance, just ZC nomenclature. And armature conductors per pole, I'm just taking it as ZA. See, in this example, 1, 2, 3, 4, 5 conductors are there. If I place one conductor in each slot, 1, 2, 3, 4, 5. In this example, 5 armature conductors are there per pole. That 5 only I'm just giving nomenclature, just simple like ZA. Okay, armature conductors per pole. Now please guys tell me, ZC equals to what is the, do you think that ZC and ZA are equal here? No. See, if you try to see in this example, do you think that 3 is equals to 5 here? No, because compensating conductors per pole in this example 3 I had taken. Armature conductors per pole I had taken 5. So here 3 is not equal to 5, to be frank. So I can write here ZC is equals to, compensating conductors per pole, ZC is equals to pole arc by pole pitch of pole arc by pole pitch means I already took this value as what? 0.8. Okay, pole arc by pole pitch of ZA. ZA means what? Try to understand. ZA means what? Armature conductors per pole. So please guys try to understand here. Here let us generally, all the conductors, if you see, they connected in so many parallel paths. That's why you should take here ZA by A gives what? ZA by A means armature conductors, okay, per pole, okay, per pole. ZA means armature conductors per pole. That too should take per path, because so many conductors are there in parallel, so many parallel paths. So here if you want, how many number of composite conductors are there per pole, per path means, here also you should take ZA by path. By ZA, you should take for one path. So you know already A means number of parallel paths. So if you want per path, ZA by A. Okay, this formula is very, very important. So one question is there based on this formula also. ZC means what? Compensating conductors per pole is equals to polar to pole pitch into ZA means what? Armature conductors per pole by, so you should take a number of parallel paths, because you are considering ZC means by default this composite conductors per pole per path. Okay, and here also if you want a per path, here it should be by total number of parallel paths. I should take it as capital A here. Okay, that distance, that A is equals, already everybody knows that number of parallel paths equals number of poles for lap winding, number of parallel paths equals 2 for wave wind. Okay guys, so let me see one question based on this formula. So this is a question asked in, I can say, yeah, GATE 1997 for 5 marks. Okay, try to see here. It's very simple question only. Yeah, a 200 volts 10 kilowatts lap wound DC generator has 10 poles. That means he has given you number of poles, how many guys? 10. And it's a lap wound. It's a lap wound. So by default, lap wound means lap wound DC generator. You know, for lap winding, number of parallel paths A equal to number of poles. If it is a simplex winding, if nothing given, you can take it as simplex winding. A equal to number of poles, that will be equal to what I can say 10 here. Okay, and 500 conductors on its armature. That means total armature something total. So total armature conductors, if you want total armature conductors if you want, that value is how much here? He has given 500 total armature conductors. Okay, right. If the pole face covers 80% of the pole pitch, means he has given you pole arc by pole pitch distance. He has given how much, guys? He has given how much is value? So 0.8 he has given. Okay. Then what is asking? The pole face conductors. That means in it is compensating conductors is asking. Okay. Compensating conductors is asking. Compensating conductors is asking. Yeah. Pole face conductors, or I can say composite conductors, required to fully compensate for armature reaction will be dash conductors per pole. That means he's asking ZC means, he's asking ZC, what is the nomenclature for the ZC? I can say compensating conductors per pole. Compensating conductors, or I can say pole face conductors per pole is equals to, I think I had given you formula. Try to remember that. Pole arc by pole pitch into what? I can say ZA by A. Try to be careful. ZA means I had given you nomenclature. What is that? I can say armature conductors per pole. Armature conductors per pole. Armature conductors per pole. Okay, per pole. Can you please tell me here total number of armature conductors means I'm having I can say 500. Per pole means 500 by, I can take here per pole. So you're having total number of poles 10. I can take it as that by 10. What about this value? I can say 50. Okay. Now please, what about total number of parallel paths? Number of parallel paths equals number of poles equals to 10. I can say 10. So please guys tell me what about ZC value? Polar pole with 0.8 into ZA I got 50 by number of parallel paths, I got number of poles, because I already told number of parallel paths equals number of poles for lap wind is a 10. So by 10, how much is value? It's a 4. That means, so what about this Judson which I had given already? Composite conductors per pole if you want. What is the answer for this question? 4 conductors per pole. Okay. Very simple question. If you understand this formula, you can easily answer this question. Okay, guys. Now, what about remaining points regarding compensating winding? See, guys. Compensating winding means we are placing in a pole shoe by having some slots. After making some slots, then only I am just placing compensating winding or compensating conductor in that pole shoe, or I can say pole face. So, but see guys, making slots and placing placing compensating conductor in those slots, I can say it is what I can say it's something process in which includes cost. It is cost for placing compensating conductors in that pole shoe or pole face. So it is very it took more cost. It took more cost. Okay, that's why compensating winding is not used in a small rating machines. To be frank, compensating winding is more preferable for large rating machines only, because this procedure needs more cost. Okay, guys. So please try to understand. Yes. So compensating winding is more preferable for large rating machines only, not for small rating machines. Try to understand that. Okay. Next, one more point here. So try to understand. Suppose example I told you I'm using composite winding in large rating machines. See, in large rating machines which are running at a high speed where loads are varying. Okay, in a large rating high speed varying load DC machines, I think very varying load DC machines. Okay, load current is a variable. Okay, so now tell me guys, whenever load current is variable, I mean to say this IA is in load current, I can say I armature. Okay, load current is variable. Load current is variable. I can say AC. So because of this load current is variable, it produces what I can say variable flux. Variable flux. I'll take it as a pi A. I'll take it as a pi A. Thereby, so I'm using one word here. Static EMF is induced in the field coils. Some people will be having some confusion here. What is that, sir? You told me in a DC machine, dynamic EMF will be induced, but here why you are saying a static EMF? So let me give explanation for that. Let us see here. No doubt, guys, in a DC machine, I'm saying in a DC machine, okay. Before explaining this point, let me please tell you basics. I already covered in basics. Please try to Let us see about RTV and RSV briefly here. I told you guys RTV means what? Here conductors are what I'm saying. Conductors are stationary. Conductors are stationary, I can say. And what about magnetic field? Magnetic field is a time variant. So whenever magnetic field is time variant, I'm saying. So depending on that only we are deciding what is the name of that EMF. If magnetic field is time variant, so I told you static EMF will be induced. What is that? Static EMF will be induced. And direction of static EMF is given by, I can say, Lenz's law. Lenz's law. Okay, guys, Lenz's law. Now let us see. RSV in a relative space variation. We know what about conductor's position here. Conductors will be here. These conductors will be. I can say what conductors will be moving. And what about magnetic field? Magnetic field, it is a time invariant. Time invariant. Okay, guys. So since magnetic field is time invariant, okay, we'll be having a dynamic EMF induced here, dynamic EMF, and direction of dynamic EMF is given by Fleming's right hand rule. That is okay. And here, after having this small discussion, let me take some simple point here. In DC machine, guys, no doubt, because of giving DC supply to field winding. I'm just going from initial stage. If you are giving DC supply to field winding, that means what about magnetic field? It's a time variant, a time invariant. It's a time invariant, because whenever DC supply is giving to field winding, magnetic field will be time invariant. So you know conductors are moving in a DC machine. Example, let me take DC generator. Conductors are moving by using a prime mover. Okay, and tell me, because of this concept, whenever magnetic field is time invariant, conductors are moving. I told you which type of EMF will be induced here. Dynamic EMF. Okay, you can say dynamic EMF is induced. So dynamic EMF will be induced. That one I'm calling it as the armature voltage EA, or I can say EZ. In generator, whatever EMF induced, that is nothing but what I can say dynamic EMF. There is no doubt in that. Okay, and because of this generated EMF, whatever the current you are getting, armature current IA, that I already told you it's a AC. Try to recollect the basics. I told you in simple loop diagram of this generator. Please try to see that. Because of generator action, whatever EMF induced in the I can say armature winding is nothing but AC. So because of the easy, whatever armature current you are getting, this is but once again AC. Okay, AC. So here my question is, try to understand. Let us see. Yeah. So now, so we conclude that armature current here is, alternating current, I can say AC current, or I can say time variant current. Okay, time variant current. Okay, so here dynamic is okay. Now after this point, this path is very important for us. So I'm getting easy value, I mean time variant, or I can say AC. So because of the whatever armature current you're getting, that is about time variant, or I can say AC. Now let us discuss. Whatever the pi A we are getting, that pi A, because of armature current, whatever the flux you are getting, that armature flux itself once again is nothing but time variant, or I can say AC. Now please let us see what will happen now. Yeah. Now what I'm saying here, in large rating machines, wherever which is running at high speed, where load is varying, okay, which produces a variable flux, thereby static EMF is induced in the field coils, okay, field coils. That means try to understand, guys. Here, whatever armature current which is induced armature winding is nothing but AC, that is okay. And because of the armature current, whatever the flux you get, that flux is once again AC. See this blue color armor, okay. This variable flux, I can say, it links with the, okay, it links with the field winding. Here I told you we are placing some field winding here. We know already in DC machine we are placing a field winding. In DC machine we are having field winding. Whenever this armature flux, which is nothing but time period, is coming and linking with this field winding. So let me laser point here. Yeah. So I conclude that in your easy is a time variant, IA is time variant, flux is armature flux is time variant. Okay. Now what I am saying is whenever armature flux, which is this blue color, okay, it is coming and linking with your field winding, which is placed on the stator. Okay. So now tell me whatever EMF induced, that EMF I can call it as a static EMF. Why? You know, field winding is placed in this is placed on the stator. So please take a field winding itself as conductor, which is placed in the stator, which is not moving. It is stationary, right? It is stationary. Yeah. Now whenever currents are stationary, and magnetic field what I can say, because of armature current, whatever the flux we are getting, armature flux pi A, I told now it is nothing but what I can say AC, no, nothing but a time variant. So whenever time varying flux coming and linking with your conductors, so whatever EMF induced, that EMF can be called as static EMF. Okay. So that's the reason why I'm using the word here statically, because some people will be having confusion why you are saying that static EMF in DC machine EMF is dynamically. No, yes, no doubt, dynamic EMF only. But after that you have to see. So after EMF induced in a generator, so which is the time variant, I can say AC, that EMF not only is a dynamic EMF. Now after that what I am saying, because of EC, whatever the armature current we are getting, that armature current is time variant, or I can say AC. Because of armature current, whatever the flux we are getting pi, that is nothing but time variant, or I can say AC. So now this time varying flux links with the, so let me write here. Yes, this time varying flux links with the field winding, which is stationary. Why field winding stationary? We know field winding is placed on the stator, no? Okay. Time varying flux, stationary conductor. So obviously you'll be having a static EMF. I'm discussing about that EMF only. Okay. Here, yes, static EMF is induced in the field coils. Now my question is, if whatever static EMF induced in the field winding, if it links with the, if it links with the, a dynamic EMF, whatever induced in armature winding, see, if this static EMF links with this dynamic EMF, I can say, okay, this and this, okay, it links with the dynamic EMF. So what will happen if this EMF which is induced in the field coils adds to the actual generated voltage, what will happen? Net voltage will increase. Okay. Now already we provide some insulation corresponding to rated voltage. If this voltage exceeds beyond the rated value, what will happen? So mica insulation will fail. I'll show you how it is damaging. Let us see. Yeah. If you see, guys, let me take this conductor. Okay, let me take this conductor. Here, here having brushes there. Here some load. Let me take this 40 amps is the load current. Okay. So if more amount of EMF is induced in a particular conductor, okay. So what I am saying here is, so you know already this one, two, this can be called as I can say complete segments. Okay, complete segment number one, complete segment number two, something like that. Okay. And between these two segments, we are providing some mica insulation here. Yes, between segment number 1 and 2, we are providing some mica insulation here. Mica insulation, okay. So suppose here EMF induced is exceeding a rated value. What will happen? So whatever the insulation I just provide between these two segments, so this insulation will break down. Is it okay for you? This insulation will break down. Whenever mica insulation will break down, so this entire voltage will appear across. I mean, once again, what between segment. I take an example of only one segment number one, segment number two, like this. Like that, you'll be having one more segment, segment number four, segment number of, 1, 2, 3, 4, 5, something like that. You'll be having so many segments. Group of commutator segments only, I'm calling it as commutator. Try to understand here. If more amount of EMF is induced in a particular conductor, so here between segment number 1 and 2, whatever the mica insulation is, that will break down. So now once again, insulation between your this entire one and segment number 1, segment number 2 becomes short circuit, okay, and this segment and this third segment will once again short circuited, because here also mica insulation will break down. So like that, total commutator segments will be short circuited, and you'll be having some flashover. So something like you'll be having some flashover will come. I can write here flashover occurs on commutator surface, Try to understand. I'm just saying very simple thing only. Try to understand. Okay. So if whatever static EMF induced field winding that links with the actual rated EMF, so here EMF it exceeds rated voltage. If EMF exceeds a particular value, so already whatever the mica insulation is there between two segments, so their mica insulation will break down because of exceeding voltage above rated value. Okay, so like that, total segments will become short circuited. I can say you'll be having some flash over will occur on a commutator surface. So now tell me guys, so this is a problem, so that happens if there is no compensating winding. Suppose if compensating winding is there, it is neutralizing armature flux here itself, it is neutralizing armature reaction itself here only. So indirectly we can reduce flashover on a commutator surface because of using compensating conductor. Yes sir, is it okay for you? Suppose if there is no compensating conductor, yes, this is the problem we are having here. If I am placing compensating conductor, yes, it is neutralizing armature reaction, it is opposing your armature flux here itself. So I can say that so flashover on commutator surface will be overcome here. So that only I wrote here. So that means, see, if this voltage exceeds beyond rated value, mica insulation will face short circuit between the commutator segments. So some flashover, see. So I can say composite when neutralize this effect by producing flux opposite to armature flux here. Okay guys. So please try to understand. So that means indirectly I can say that, so whatever flashover at the commutator segments I got, this can be reduced by using compensating winding. Is it okay for you? So this is one way of explaining. So we can explain in a different way also. I already told you guys in armature reaction, because of armature reaction, we got ME, magnetizing effect at trailing pole tip. Do you remember that? I'll show you a figure once again. In generator coils at a trailing pole tip curves maximum value of flux. What is the reason for that? So you guys try to understand. I can tell this, I can explain this point by using these waveforms also. See, at a trailing pole tip, in generator point of view, in trailing pole, I told you maximum, ME effect you are having, magnetizing effect is there. So that means more amount of flux is there, at the trailing pole tip. That means conductor cuts more amount of flux. Whenever conductor cuts more amount of flux, you will be having more amount of EMF will be induced in a conductor which is on trailing pole tip. That means, whenever EMF induced is more in the conductor which is on trailing pole tip, if it exceeds a particular value, once again, whatever I explained here, mica insulation will break down, flashover will come on the commutator surface. Okay. So see, the magnetic effect is the trailing pole tip. This is I already explained by using waveforms. Or if you want, I will show you this one also. A trailing pole tip magnetic effect is there. Maximum amount of flux is there here. Okay. So whenever conductor curves this maximum amount of flux, so that means indirectly EMF induced in a conductor which is under the trailing pole tip will be more. If that EMF exceeds a particular value, so obviously, yes, commutators, whatever the mica insulation between commutator segments, so that becomes the short circuited, flashover will come. So let me show you that point here. Yes, in generator coils, a trailing pole tip cuts maximum value of flux. Therefore, maximum voltage is induced in those coils. If this induced EMF exceeds a rated voltage, I told you mica insulation fails, short circuit of intercommutator segments, take place, it results in a flashover and cut complete segments. This can be reduced by using compensating winding. So guys, what is the conclusion here? So regarding compensating winding, you have to remember guys, very important points. I can examination point of view, these are the points they are giving. So let me write here. So these are the points I can conclude regarding compensating winding. Compensating winding, where we are placing compensating winding? Tell me first of all, compensating winding is placed in I can say slots which are made under pole shoe, which are made under pole shoe, which are made under pole shoe. Can say okay, this is nothing but in main poles. Whatever pole shoe is there, in that pole shoe I had to make some slots. In the slots I had to place this compensating winding. Next, compensating winding is connected in series with what I can say, in series with armature winding, the second point. And compensating winding, I can say, reduces the demagnetizing effect indirectly. Wow, because this compensating winding is placed along polar region. So under, I mean, whatever the flux is reduced under each pole, so that effect was the overcome here because it is neutralizing armature reaction itself. Okay, it is opposing your armature flux, who is responsible for having armature reaction. So that means indirectly compensating winding neutralizes armature reaction, okay, along polar region. So in this formula also, easy means pi to be 60. In this formula, pi means average value of flux per pole. So here whatever the per pole, whatever the flux, average value of flux per pole is there, okay, so that flux was reduced because of armature reaction. Now, because of placing a compensating winding, it is opposing your armature flux. That means it is neutralizing armature reaction here itself. So that means indirectly compensating winding reduces DME, demagnetizing effect. And one more point, see, the compensating winding is used for large rating machines only, and compensating winding reduces flashover at commutator surface, it reduces flashover at a commutator surface. Okay, is it okay for you? Yeah, there is no need to confuse this arrangement guys. I think some people will be having some confusion with this arrangement. Nothing here, is very simple thing only. Let us see, because we already I think already we have in the simple loop diagram of a generator, we already saw this diagram. Let me show you once again, excuse me. Yeah, so already I just showed you, it's north pole. Let me take here ABC is a coil, okay, and here south pole, okay. So let me take this portion here. Here I just provide some mica insulation, segment number X, segment number Y, brushes here. If it is generator, let me cut some load here. Okay, this diagram already know. So I'm saying if more amount of EMF is induced in a particular conductor, so from this conductor only current is coming to the load through, I can say, segments only. Okay, so if more amount of EMF is induced in a particular conductor, so I'm saying if it exceeds the rated value, if it exceeds rated value, so whatever mica insulation between the segment number X and segment number Y, it will be damaged. So that's the reason this portion only, see this portion, see, if you see in the segment number X and segment number Y, I just placed a coil. In segment number X, I just placed in this one side of your coil, other side of your coil I just placed in segment number X. So this portion only I just drawn here. There is nothing, you see. If you take this segment, yes, one side of your coil is a coil. Let me take this one as a coil here, okay, and another side of your coil is this one. So here say like a X segment, Y segment, I'm having segment number 1, segment number 2, here I just placed here. And between segment number 1 and 2, I'm having some mica insulation. So that will be damaged if more amount of EMF is induced in a particular conductor. Okay. So guys, there is nothing new here. So there is no need to confuse. Okay. So this is regarding your compensating winding. Okay. So these are the points you have to remember for examination point of view. This is one more question asked in GATE 2000 for 1 mark. So please try to answer this question. The compensating winding is in a DC machine is located in where? Tell me where you are placing compensating winding. So tell me, do you think that I'm just placing compensating winding in armature slots? No. See, here compensating winding is placed in the slots which are made under pole shoe of your main pole, not in the armature slots. Is it okay for you? So I'm not placing your compensating winding not here. It is here. Okay, so option A, it is located armature slots for compensation of your armature reactions is wrong. Let me go for option B. Is located on commutating poles. There is nothing to confuse. Commutating poles means interpoles, which we'll discuss in the next class. There is no need to confuse. It is compensating winding is not located on a commutating poles. Is not located in interpoles. So option number B is also wrong. Suppose let us say option number C. Is located in pole shoe. Yes. For avoiding the flash over at the commutated surface. No doubt. Option C is correct. So guys, please let me go for option C. So let us see option D also. It is located in pole shoe. Okay. To avoid sparking at the brushes. No. So for reducing sparking at the brushes, for reducing the CME, we should use interpole winding or shifting of brushes along MN. That is what different approach. Okay. So to avoid sparking the brushes, we should use interpoles, not compensating winding. So option C is correct. It is located in pole shoe for avoiding flashed over or completed surface, which I already explained. Okay, guys. So now in the next session, I'll discuss the commutation topic, because if you want to explain the interpole. So first of all, interpoles are used to reduce sparking of the brushes. First of all, you should know why we are getting spark with the brushes. That means for explaining why you are getting spark with the brushes, I should explain the commutation. To be frank, because of under commutation, because of poor commutation, we'll get spark with the brushes. That means I should explain the commutation topic. So then I'll tell you what is a good commutation, what is poor commutation, what is under commutation, why we are getting spark near the brushes. So then we'll see. So to reduce that spark near the brushes, I should use interpoles or compoles. We'll explain that topic also. And regarding that, we are having some more questions. So here, okay, we'll see those things in the next session. Okay, guys. For this session, I think a compensating winding, okay, is enough. And in the next session, I'll start the commutation topic. Okay, if it is possible, I'll take this one. What is it? Interpol topic also I'll take. Okay, thank you.